So thanks everyone for coming. Welcome to the IGERT program on Ocean Change Winter Seminar Series. The IGERT program explores ocean change from a multidisciplinary perspective and is funded by NSF and GSAO. Just a reminder, there's a reception after today's talk if you'd like to stick around. And next week we have Jack Kittinger, so Tuesday, same time, same place. So today's speaker is Joughin. He's a glaciologist working at the Polar Science Center to determine how the flow of Greenland and Antarctic ice sheets contribute to sea level rise. He's used a variety of tools to explore this problem, including satellite data, ground and airborne data, and on site. He's traveled to Greenland and Antarctica more than a dozen times in the last decade, and he's also used ice sheet models to determine the physics that control ice. Ian did his graduate work at the Polar Science Center, getting his PhD in electrical engineering from the University of Washington. And during his graduate work, he developed methods to measure topography and ice flow in Greenland. After his PhD, he moved to Pasadena to work at Jet Propulsion Laboratory, where he continued to work on interesting problems, including writing algorithms for the Shuttle Radar Topography mission. After 9 years with JPL, he returned to the Polar Science Center, where he's now, and he's also has an appointment in the Department of Earth and Space Sciences. One thing about Ian, in 2012 he won the EGU Louis Agassiz Prize for fundamental contributions to our capabilities to observe and interpret ice dynamics. And his award went on to say, Joughin has helped transform glaciology from a data-poor field where challenging logistics limited what we could know to a field where satellite observations allow detailed study. His work has been hugely important. The award goes on to say, his contributions have helped play an important role in convincing the broader scientific community, policymakers, and the lay public that the Earth's ice sheets are variable on human timescales, not just over millennia. So I'd like your help in welcoming Ian, who's going to talk about ice-ocean interaction in Greenland and Antarctica.
So I'm going to talk about ice-ocean interaction in Greenland and Antarctica, and more from the way the ocean affects the ice sheet. For example, I'm not going to talk about fresh water from Greenland affecting North Atlantic circulation. So, as Stephen mentioned, I do a lot of work measuring the flow speed of glaciers. This is actually, we have much better maps now. This is an old figure. But this is showing the speed of the ice in Greenland. Essentially, the way an ice sheet works is snow falls on it, and it piles up till it begins to flow under its own weight. In Greenland, that can be, its thick is about 3,300 meters. Richard Alley wrote a book titled, it's about 2 kilometers. He wrote a book called A 2-Mile Time Machine to describe the ice cores that reflected right in the middle of the ice sheet. So this snow piles up and it flows out toward the edges, where one of two things happens. The ice melts in situ and then runs off, either right off the surface of the ice sheet, or more often it actually runs into a deep moulin and penetrates through the ice and lubricates the base and comes out, which is an interesting story in itself. Unfortunately, I don't have time to go into that much today. But it also calves off as icebergs. In Greenland, it's about 50-50, half iceberg calving and half melting. In Antarctica, it's also 50-50, but things are upside down. So we still have the iceberg calving, but in Antarctica, the ice sheet flows out over the ocean, and there's very little melting on the surface of the ice, but underneath the ice shelves, there's large areas in contact with warm water, and they melt. So about half of the ice shelf melts, and about half of it breaks off the front and flows away. And you can see there's quite a range of speeds, and in the middle, where it's just collected a little bit of snow, it's only moving at a few meters a year. Down here, it can be, as I'll show later, more than 10 kilometers a year. And most of these reds of glaciers up in here are moving at about 1,000 to 3,000 meters a year as they get sort of extruded through these narrow fjords. So this is just a little picture of what melt on the ice sheet looks like. This is maybe what people normally picture. People talk about ice sheets melting, but just as often they're not melting there, they're floating away somewhere else after they've broken off as an iceberg. This is the terminus, and I'll talk a lot about basically I'm talking about the calving face when I say terminus, where these large icebergs break off. If you saw the Chasing Ice movie, this is where these icebergs broke off from. Big icebergs like this, and they can actually, large sections of this can calve all catastrophically. I think in Chasing Ice it was about 75 minutes for about a kilometer worth of ice to come off in several 100-meter slabs. So these are really dramatic events. This glacier is also infamous for probably being the glacier that put out the iceberg that sank the Titanic. So ice sheet mass balance then, of course, is the balance between the snowfall and the melt and iceberg calving. And sea level rises and falls when this balance is disturbed. So during the last glacials, Greenland and Antarctica were much bigger. The sea ice was sea level was much lower. The Bering Land Bridge opened up. Now we're worried about the opposite problem of losing more of the ice that's there and sea level going up. And right now, to put things in perspective, Greenland's about 50% out of balance. So there's about 50% more melting and iceberg calving than that's been balanced by snowfall each year. Just to give you an idea what a meter of sea level rise looks like, this is what southern Florida would look like. Large, it's hard to see in here, but it's a big, really not expensive coastline that would disappear. There's already been stories in the New York Times about various businesses that are having water come in more and more frequently. One thing that's actually often not thought about sea level, but sea level is not a fixed thing. It actually can vary by huge amounts. So if you're kind of on the upper edge of that, water then starts. It's sort of a 30-centimeter variation. No, it's more than that here. But anyway, there's a large variation you can get, and there is quite a bit of inundation occurring already. The IPCC, or the Intergovernmental Panel on Climate Change, estimates somewhere between a quarter to a meter of sea level rise over the next century. A quarter is almost certainly too low, as we're already seeing about, from altimeters we know over the last decade or so, we've had about, increasing at about a rate of 3.3 millimeters per year, or 0.33 meters per century. There are plenty of people who will say that this is too high, but there's some who will also say it's too low. It's generally a rule of thumb. People think about a meter, give or take a little bit. About a third of this is due to thermal expansion, and much of the rest is from melting ice sheets and glaciers. So ice sheets are about a third of the current sea level rise, and glaciers such as we have around us and in Alaska, all of the ice outside of Greenland and Antarctica contributing to about a third of that 3 millimeters. And we know when things were warmer, prior to the last ice age, we had about sea level about 5 meters higher, and there's still a lot of debate going on about how much of that came from Greenland and how much of that came from Antarctica. There's good reason to believe that both ice sheets would have lost quite a bit. So David Joughin put these nice graphics together showing the height of the ice sheets. Again, it was about 3,300 meters in the center of Greenland, and it's more than 4 kilometers thick in the center of Antarctica. And by the way, I think these are the scales, so this is what Greenland looks like relative to Antarctica. There's about 7.3 meters of sea level rise locked up in Greenland, about 57 in Antarctica, and the part that's the most concerned is this little line West Antarctica, much of which is sitting on the seafloor, many hundreds of meters below sea level. Hence it's termed a marine ice sheet, and the whole West Antarctica has about 5 meters of sea level, but the unstable parts that are likely to go quickly are believed to be about 3.3 meters, or about 10 feet of potential sea level rise. And then glaciers and ice caps, the total reservoir of ice there is actually only about 15 centimeters to 37 centimeters. So that's why there's been, even though now the contributions are roughly equal, there's been a lot more emphasis on the ice sheets because there's not that big a reservoir in the glaciers and ice caps. So this is a quote from the fourth IPCC, and basically they said that they couldn't put an upper bound on the contribution of sea level rise. And what happened there was they were using ice sheet models and making relatively conservative predictions. At roughly around that era, people didn't we knew the ice sheets could contribute to sea level, but we didn't know how fast the glaciers could respond. We thought they responded slowly. I like to often say in talks that when I started, I got out of grad school and I was mapping velocity. Someone said you'll map the ice sheet velocity once and then your career's over because the glaciers aren't going to change on the scale of your career. But fortunately, the ice sheets are good for my career anyway, not for society at large. When they were writing this fourth IPCC, myself and several other groups started observing large changes and large speed-ups of many glaciers, and I'll show some examples of that. And they were stuck with a model that shows one thing and observations that are showing another thing, but they didn't have any way to quantify that or get that back into the models. Since the IPCC is essentially a large literature review, it's not like they could do a lot of stuff on their own. So they more or less had to publish the more conservative model estimates and just sort of put an asterisk by them saying we really don't know what the upper limit is. The fifth IPCC has, things have calmed down a bit. We sort of understand a lot more about what's going on with the glaciers and the processes that are controlling them, but we still don't have all of that fed into a model that we can spit out an estimate with a certain accuracy or uncertainty. So there's still caveats in there, but they're not quite so dire. Oh, and one of the big problems was interactions with the surrounding ocean. Traditionally, the way the ocean is in sort of long ice age cycle simulations, the way the ocean forces the ice sheets often is just that as sea level goes up and down, it sort of floats the ice sheet up or down and has an effect that way. But that's not a very big effect on the time scale we're looking at when we're talking about millimeters a year. Instead, what we're seeing is that the melting by the ocean, which was really not recognized, not even put into many models a decade or two ago, really is driving a lot of the change. There's also some uncertainties about glacier basal conditions. Some of those we've cleared up a little bit. We now know that the lubrication on the Greenland ice sheet is not going to cause it to go slip sliding away anytime soon. So, got a series of cartoons. I hope they're not too busy to try and sort of demonstrate that from over here. So this is an ice sheet flowing into the ocean, and here's the interface with the ocean. And if you integrated the pressure in the ice, this down, and you integrated the pressure in the ocean, you'd find that the pressure from the ocean pushing on the ice face is less than the ice pressure pushing out. So there's a net sort of force pulling the ice out from the ice sheet, and that force has to be balanced by basal traction upstream. And because we're dealing with nonlinear viscous material, it's going to depend on the strain rate and longitudinal stress gradients, which basically mean gradients in the velocity. That tugging is going to lead to sort of an upward increase in velocity toward the terminus and a stretching of the glacier there. There's also the traditional driving stress, driving the flow, which is basically the surface slope times the thickness and then gravity and density of ice. Essentially, it's not a real stress that's applied anywhere. It's basically, again, the column averaged pressure difference at any point, I think, depending on this surface slope and thickness variation. So the ice needs to have enough friction at the bed to accommodate both the terminus pull, which generally would extend about 10 ice thicknesses upstream. So for a kilometer thick terminus, that effect would be about 10 kilometers upstream. And then above that, it's mostly the driving stress. So it does have to have this extra basal traction here to accommodate the terminus. There's also what you may have heard of the ice shelf buttressing effect. So we can have two ice shelves here, one with an ice shelf and one without, otherwise the same geometry. And there's a couple of different ways the ice shelf can go. It could be extending out into the ocean with no contact with any rock. And there's the Mertz Glacier tongue and some other big ice tongues in Antarctica that stick out of the ocean. And for all practical purposes, we just assume there's zero friction between the water and the ice, so that the ocean is not providing any friction. And if you actually integrated the pressure difference all the way up the ice shelf here, you'd find that it all ends up being equivalent to the pressure difference here. So you could lop off this ice shelf and the glacier would not care at all. You would get no response from the ice sheet itself, the grounded ice. So those are dynamically equivalent. What's not equivalent is if you actually have an ice shelf and you're jutting out into an embayment. In the case of the Ross, it could be the Ross Sea embayment, which is straining an ice shelf the size of Texas, or it could be a very narrow fjord, like an outlet glacier in Greenland that might only be 5 kilometers wide. But in that case, the drag is supporting some of this stress here, so it's resisting the flow, which is basically very much like a buttress. You could build a church, you could put a lot of heavy columns inside to support the weight of the church, but you have a crowded church, or you could distribute some of that load out to the flying buttresses on the outer side. Of course, if you go with that approach and then someone removes your buttresses, your church will fall down. And similar with the ice sheet, if it's evolved to have an ice shelf there, and that suddenly goes away, then the ice shelf the ice sheet's going to start flowing rather rapidly. And that's one of the main things about the ocean is you can have mechanical changes very quickly. If you had something on land happen, the ice might tumble out of there, but it can't go anywhere. The ice sheet would still have to bulldoze it out of the way. But with an ice shelf, something like the Larsen B ice shelf can break up in a matter of weeks and just disappear, and all of a sudden that big buttress is gone. So back to the ice-ocean boundary. So basically we have our sidewall traction. That means, again, we can build a steeper ice sheet than we might have otherwise built based on the available friction at the bed. So then, like I just said, when we get rid of that for some reason, we have to have more basal traction. The speed of the glacier is proportional to the basal traction raised to some exponent and nonlinearly. And so small changes in traction can lead to large changes in speed, or you need to speed up a lot to balance to get enough basal traction to balance things. And the other thing is this force at the front, it's proportional to the thickness or depth of the water here squared. And if you retreat into deeper water here, you get a bigger pulling power. And you can imagine, you can see the feedback here. You retreat into deeper water, you get more of a force. You have to speed up to balance that. That stretches the glacier more, that thins it out more, and it wants to keep going back. And that's essentially what leads to the marine ice sheet instability, which was first put forward by Mercer in the 70s. And let's see if I can walk through this with some figures I've adapted from Christian Joughin. Although this is figures for the marine ice sheet instability, it actually is in some ways more like the situation in Greenland, where you have a bed that's above sea level, and then you have areas of the bed that are below sea level. So back to this, basically the terminus speed is nonlinearly proportional to the thickness here. So, and at this point, the way he set up the figure, we're just assuming that effect's gone when it's out of that the ice is slowing way down when it gets out of the water. So it's basically showing 0 here, but there would be some actual speed. So this shape here is reflected in this nonlinear function of speed at the grounding line, or the flux into the ocean. That flux flowing into the ocean has to balance the amount of snow falling, and if we had a constant accumulation rate all along the ice sheet, as it goes along, it picks up more and more snow, so we integrate that toward the coast. And for any of these ice sheets, this would be the flux from the snow at the grounding line that would have to balance the flux across there. So the ice sheet is going to be in balance. The flow across the grounding line is going to be in balance with the snowfall at points where the flux equals the accumulation. But they're not all the same kind of equilibriums. In this case here, where the ice sheet is grounded on a forward slope, if it starts, some perturbation causes it to go forward, it's going to speed up, and that will cause it to retreat, and it'll come back to this point. Similarly, if it starts to retreat, it'll slow down, and then it will re-advance to this point. So that's what happens here. At this point, if it retreats into deeper water, as I was just giving in the other example, it will start to speed up and thin more and retreat back, and it'll keep going back. And similarly, we have a more stable point here. So you could imagine in this case, if you had this ice sheet, it would start to retreat, and it would keep retreating until it actually got back to some stable point like this. And that's generally what is likely to happen with a lot of Greenland outlet glaciers. As they pull out of their troughs, they will find a new stable, a smaller stable ice sheet. But with a marine ice sheet, you more or less have a slope that goes all the way back to the interior of the ice sheet. There might be little bumps on here that slow things down for a while, but in general, there's just this one position of not real stability here without an ice shelf anyway. And if you perturb that, the next stable state is essentially no ice sheet, because the flux across the grounding line just keeps growing as you retreat in, and you have less and less snowfall as the area of the ice sheet decreases. So that buttressing effect can actually stabilize that. That's why we do have an ice sheet in West Antarctica, even though it's not a very stable position. The ice shelf can take up some of that stress and slow things down at the grounding line and provide a stable point. And then that's where the ocean comes in, and I'll go through both of these in a bit more detail. But there's on the ice shelves in Antarctica, you've got melting beneath those, and you've got lots of fjord and ice melange in Greenland affecting things. So the ocean can force the ice sheet, but because of these kind of unstable dynamics, sometimes it doesn't take much of a perturbation from the ocean to actually force the ice sheet to go into an unstable retreat. And so it's essentially the shape of the bed here that controls the ice sheet's response. So in Antarctica, for marine ice sheet, you might expect this to go all the way back, whereas in Greenland, you might lose this slug of ice from unstable dynamics, but you get, again, a smaller, more stable ice sheet once it retreats up into the middle of the ice sheet. So now I'm going to talk a little bit about two focus areas that sort of more illustrate these points. And I'm going to talk about Jakobshavn Isbrae, which is the largest glacier in terms of discharge volume in Greenland. And I'm going to talk about Thwaites Glacier and a little bit about Pine Island Glacier. These are glaciers along the Amundsen coast. So first, tidewater glaciers. This is the embayment that the glacier flows into. So I just showed you earlier the cabin front along here, so ice is flowing in here. There's another branch here, but in the late 90s and for the century before that, this whole fjord was filled with ice about 300 meters thick. Now it's only filled with bits of iceberg and sea ice, which in the winter freeze together, and it's often referred to as melange, this material. So in the winter this would be a rigid material, and in the summer it's just all free floating around and can move easily. So I'd mentioned that when they were doing the fourth IPCC, there were lots of speed-up events, and this is one of the bigger ones that taught us there's a lot we didn't know about glaciers. So these points each show a point along the main central flow line along the center of the glacier, and they're color-coded by the coding here. And I'm mostly just going to focus on the red points, which are the ones that are closest to the terminus. So in the 1990s, we only had a few points, but things were pretty stable. And actually in the 80s, a field party went out there and tried to look for seasonal variation. They couldn't really find much substantial seasonal variation, and the speeds were pretty consistent. But in the 1990s, late 1990s, the floating ice tongue broke up, and I'll show that in a second. And things continue to speed up as we begin tasking satellites to collect data on this regularly, so we have a much better time series. Right now, this is by far the best time series we have for any glacier. It's not representative of the density we have. We might have 40 or 50 measurements which cover 11-day periods and overlapping 11-day periods on Jakobshavn. In many of the glaciers we have 5 or 6 measurements. Some glaciers we have none. And then things really took off in 2012. The speeds peaked at this point at something like 17 kilometers a year, which as far as we know is, at least for the ice sheets, the fastest speeds ever observed. There's probably a few surging glaciers in the mountains that briefly peaked out faster than that. But this is actually showing more than 4 times the annual speed then. If you look at the mean annual speed, it's about 3 times greater than it was And the subsequent summers had strong peaks as well, and I'll explain a little bit why they aren't quite as high as in 2012. The other thing I want to emphasize is that this is not meltwater forcing. This is going into, as I'll show you, it's a function of the terminus position. There may be a little bit of a lubrication signal on here, but it's probably a couple hundred meters a year at most, not the nearly 6 or 7 kilometer per year signal we're seeing in the summer. Let's see if I can run this. So this is a time-lapse video that Mark Fonstock and Martin Trufer put together. It was positioned not that far from the extreme ice or chasing ice things, but it's basically going to show the position of the terminus through the summer of 2011. You can see various calving events and advances, retreats, and then at some point it starts going way back really quickly, and it ends the summer 5 or 6 kilometers farther back than it started. So there's a seasonal variation in the terminus position, but there's also a longer term trend. This is 2000. These are now synthetic aperture radar images. They look like black and white photographs, but they're actually radar imagery, so you're seeing scattering at radar wavelengths, not optical wavelengths. This is the floating ice tongue. It's about 15 kilometers long, and that was in 2000. It started to break up with some large rifts along the side here. By 2006, most of that shelf was gone, and in the summer we did get a little bit of a floating ice tongue, or in the winter we got a bit of a floating ice tongue that formed, but it would retreat back each summer, and that continued. And then in 2009, we didn't get any seasonal floating ice tongue. Mostly it was a grounded terminus that was advancing. What I'm showing here, by the way, are the late summer positions, so the most retreated position each summer. And you can see each summer it gets progressively farther inland. So every summer it's about 600, 800 meters farther back than the previous summer. And at that rate, 600 meters a year, the fjord's about 60 kilometers long, so it's about a century worth of retreat it could sustain at those rates. And the rate of thinning is actually also comparable to what it would take to bring this whole glacier down in a century. These are zoomed in again on those velocity points, and I just want to show the comparison between, so these black points are the retreat, and up here means more retreated, so you can see the seasonal variation I just showed you in the time-lapse thing, and then here's the trend we just went by looking back. And then David Sheens began putting together some nice maps of thickness. So this is the elevation of the glacier through time, and you can see there's an overall downward trend, but you get much more thinning in the summer, and that's when the glacier is speeding up, so it's stretching out. And it actually compresses, even though it's still stretching in the winter with the thickness gradient, it ends up thickening a little bit in the winter and thinning again in summer. But overall, the trend is down, and you can see up here, maybe a little over 200 meters, and we're down at 140 meters after 3 years. And you can see that thinning signal here again, where the 1990s is shown in black, and then 2009 in green, and then 2012 in red, and then this blue line is the height the glacier has to drop to till it starts to float. And the dashed line here is the bed topography as we know it, and then these points are essentially these points here, these terminus positions, and they're plotted with a color by the day of the year, and you can see generally the red points in the middle of the summer tend to be the farthest back here, and here's the year here. So the interesting thing is that in 2012, the farthest retreat back is right over the deepest part of the trough, and then the 2013, where I showed you that point was actually, it was slower the next summer. That's because it very quickly retreated over this part, it looks like, and actually now it's starting to slow down. So all of the stuff I was showing in the cartoons, the way things should behave is exactly the way this glacier is behaving, which is reassuring because we know that it wasn't, we understand at least the process that's going on. We actually know what the bed topography is like. We haven't fully rigorously modeled it at a high resolution, but we know that it's probably not going to be just increase its speed indefinitely, as maybe the concern was earlier. We can actually use just a very simple model where we look at the observed speed, these blue dots, through the course of the year for 2009 and 2006. And then the green dots and the red dots are just a very simple model where we scale the extra stress from the terminus by the mean annual stress, and just use a scaling argument to show that the terminus position can actually predict the annual variation in speed quite well. Gets a little bit weird here, but that's not surprising given there's a lot of thinning going on over the course of the summer that we didn't include in the model. So the terminus controls the speed, but then what controls the position of the terminus? And that's where things become much more murky, and we have some ideas, but it's far from a solved problem, and there's lots of challenges and areas for glaciologists and oceanographers to work together. So these are the sorts of things that are happening in the fjord. There's Erminger water, Atlantic water, this warm current getting into the fjords. There's this ice melange here in front of the glacier, which stiffens up in the winter, which is going to depend on atmospheric and sea surface temperatures. There's melting along the face of the glacier here, which is not clear exactly. It seems to have an effect, but it's not clear exactly why, because the glacier might be moving forward at 20 meters a day, so it's not clear what 1 meter of melting would do to change that when these big 100-meter icebergs are catting off all the time. There's also potentially warm water in the fjord all year round, but in the summer you've got this melting going on the surface of the glacier. It gets beneath the glacier, it flows out, and it comes out the front of the terminus, so you have this buoyant freshwater plume going. So even though the warm water is there year round, you might have much more melting going on in the summer. And there's Adrian Jenkins had some papers showing nicely that can increase the melt rates quite a bit. So let me first look at the ice melange, which again is all of this ice in front of the terminus. And it occupies, again, this whole area where the former ice tongue used to be. This is a bit of a busy figure. So basically we're looking at the 30-year temperature in black, and then the magenta colors are just the monthly temperatures, mean monthly temperatures. And you can see that the winters have been quite a bit warmer in Greenland. The summer temperatures have gone up some too, but it's actually about 5 degrees warmer on average in the winters now than it was in the 80s and 90s. And the yellow curves just show the terminus position with time. And I'm just going to zoom in on this interval here. Here we have a sequence of images, and there's all this melange in the fjord. It's pretty much the same. In fact, when we cross-correlate these two images to produce the velocities, we can see the melange being pushed down fjord sort of rigidly by the front of the glacier at about the speed of the glacier. So this is really locked up, and it doesn't actually have much structural strength. It's not itself slowing the glacier, but I'll show in a second why it is important. And then around this interval, things either got warm enough in there to sort of break things up, or it just, like a log jam, the dam broke and all of the ice started to spill out. And you can see all of this is moving down the fjord. At this point, we couldn't make a map like this because everything is moved and is completely random, so we can't track it down the fjord. But that's that period here where that also corresponds to exactly when this terminus started retreating a lot. So it seemed to implicate the melange. When you've got rigid melange, you don't have much calving. When you have everything's mobile and swept out of there, then the calving happens. And Jason Amundsen, you may have seen his talk last year. He was a candidate for the ESS position, but he's done some really nice work showing why a little bit of fairly weak melange. I mean, we're talking the sea ice bonding melange is a few meters thick, and we're looking at something 1,000 meters pushing it. That's why it doesn't have a lot of strength. But if you've got the glacier sort of breaking up these slabs, they may even have sort of, over the course of the winter, the slabs may even have broken apart some, or they're heavily fractured. They want to roll out of there, but you've got the melange just pushing back a little bit, and it just makes it hard to roll the icebergs out of there. And you don't need much of sort of a line force applied up here to stop these icebergs rolling, but when you sort of take that away, then things topple out like dominoes, and that's exactly what happened in the Chasing Ice video for Jakobshavn. They just, and I don't know if you've seen the video where he overlays like the southern part of Manhattan on the glacier, but it was a huge event. I mean, it's like all of Manhattan tumbling into the sea at once, except these icebergs are much taller than the skyscrapers. So there's really impressive events, and they actually get picked up often on the Global Seismic Network. Meredith Nettles had some papers showing many of these big calving events are equivalent to magnitude 5 earthquakes. So that was sort of how melange can change things, and we do know that in the 80s the sea ice was very thick, which would have bonded the melange together much more in Disco Bay, and they were able to take the sled dogs across to Disco Island regularly. And then in the late 90s, early 2000s, there's a lot of open water in the winter. They could no longer do that. You could probably plot sea ice concentration against sled dog population and find a correlation. Because there's every time I go up there, there's less and less of the Greenland huskies penned up around town. So melt from the ocean can be more important. I mentioned that along a vertical calving face, it's not impossible, but it's harder to see exactly how that would have an effect. But when you have a 15-kilometer ice tongue and melt rates of, so a huge extended surface in contact with the ocean, way more area, and melt rates of 1 meter per day, as Roman Matika has shown, you could actually start to thin things. And if this ice tongue would have been in equilibrium with some sort of melt rate, maybe it was 0.5 meter a day, and maybe it went up to 1 meter a day, because there is a tremendous amount of ice coming in here, but that could have thinned and weakened the shelf and led to its breakup. Whereas the melange, what may have happened is seasonally may have been shorter, the period where it's suppressing calving, so there may have been more calving. Somehow these two effects, which we haven't fully separated yet, likely contributed to the breakup of the ice tongue, which then caused the terminus to speed up. David Hollins looked at, looking at a 300 or so meter thick ice tongue. Actually here it's thicker than that. He's looked at the water at those sort of depths. In 91, you can see it was quite cold. And then into the 90s, it warmed up, and it's been pretty consistently warm ever since. And so, see the reds on this are 3 to 4, reds and yellows are 3 to 4 degrees, whereas it was down around 1 degree before that. So that's quite a bit of warming that could drive a lot of melt. And before I leave Greenland, I want to point that these are not isolated. Jakobshavn is not some exceptional glacier. I mean, it is exceptional in many ways, but many other glaciers are speeding up. In Greenland, this is a map that Twyla Moon put together before she graduated that shows roughly 200 glaciers around the Greenland coast at a couple of different time intervals, and you can see the speed up. Generally, the speed up is in red, and blue are slowdowns. Things don't always speed up. For example, a glacier might retreat into shallower water, but in general, there's a lot more speed up than slowdown, and overall, the glaciers in Greenland collectively have sped up by about 30% over the last decade or so. And again, with Greenland, Matthew Malham recently published this work. It's showing that a lot of the troughs only extend in a little ways in here. So all of these potentially dynamically stable states, the glaciers can retreat out of their troughs and at least dynamically be stable. That doesn't mean more melting won't remove the ice sheet over time, but it would reduce the iceberg, any kind of dynamic instability, which is good news, and it means Greenland shouldn't just dynamically slide away. We can actually see in the southwest part of Greenland, you don't see a lot of deep troughs here. Much of the ice sheet has actually receded out of its fjords, and if you look at the velocity map, you won't see many of those red colors. There's really fast speeds in there. There's a couple glaciers, but by and large, much of the glacier is just terminating on the land and melting away, or has wimpy little glaciers that are just slowly discharging ice to the ocean. So, to summarize Greenland before I go to Antarctica, the tidewater glaciers, our sense of ice-ocean interaction is the water's warm, but, and it does seem linked to the amount of terminus retreat, which we can sort of, and it's linked to warm, or correlates, but then the issue of correlation and causality kicks in, and we're not really clear about, the role of melange, the role of melting, and there's other processes that aren't directly ocean related. For example, if you have warmer air temperatures, you get more water in crevasses, which would tend to have more hydrofracturing, which could contribute to greater calving. And then the other thing to remember is I guess, sort of like a tipping point. Once many of these glacier instabilities are triggered, they may just respond to their own dynamic instabilities without necessarily a lot more forcing from the ocean. And yeah, this exact role of the ocean forcing is still a very challenging research problem. And some of those challenges are, again, the multiple correlated forcings. So all of these things happen at the same time. Surface temperature, sea surface temperatures are warmer, temperatures of depth are warmer, the atmospheric temperatures are warmer. The ice dynamics, again, if the ocean did something 5 years ago and we're looking really at an ice dynamic response now, it's hard to support, tease out all the different effects. Iceberg calving is sort of a holy grail problem in glaciology. It's a very difficult fracture mechanics problem. It may be more as fruitless trying to do that as predicting earthquakes, and for similar reasons. And these areas are logistically difficult to access. You wouldn't want to be in a boat putting out a CTD in front of Joughin when one of those big icebergs rolled over. David Holland has flown around a lot in front of the glacier, dropping XCTDs in from helicopters, but it's a rare day when he can find open water to drop one of those through. That's near the calving front. The outer fjord he's got quite well, but he doesn't have a lot near the terminus of the glacier. And then the bed and fjord geometry are poorly known, but that's getting a lot better with like the map I just showed from Matthew Moynihan. So let me switch over to marine ice sheets now, and before doing that, let me just sort of frame the problem differently. So this is the Joughin Basin. It's about 60 kilometers long, this main fjord trough where the ice is now. It's very deep, about 1,300 feet, up to 1,300 meters deep, but it's sort of a very narrow slot. And again, it does peters out as you go toward the interior. In Antarctica, though, West Antarctica, you have this marine basin. You've got the scale cuts off at 2,000 meters here, so you have very deep seafloor that the ice is sitting on. I'll show a little bit more detail for this area now, but it's not quite the smooth basin that sort of the early Mercer papers envisioned. There is topography in there, but in general, it's back sloping toward the center, which should subject it to the marine ice sheet instability. At least in Greenland or in Antarctica, we have a bit better understanding of how the ocean would affect the ice sheet. We know that if we thin this ice shelf, that it would reduce the buttressing, and that's pretty easy to put into a model, comparatively easy to put in a model. If you could tell me what the melt is along this ice-ocean interface, which is a challenge in itself, but then I can tell you what the response of the ice sheet would be over time. There's different kinds of melting going on. There's the sort of the classic ice pump here, where you have sea ice in front of the glacier. It freezes, you get dense, high salinity brine going down under the glacier. It's minus 1.9 or something, the surface melting point, but as you go down here, the temperatures, the pressure melting point changes so that you're about a degree above the pressure melting point. You can melt ice, but actually, even though you can melt ice, what kind of goes up must come down. As that water goes back up, you're going the opposite way against the pressure melting point, and you get a lot of refreezing. The Filchnirani ice shelf, much of the middle of the ice shelf, is about half meteoric ice that slid off the land, and about half of it's ice that froze at the grounding line and then refroze in the middle of the ice sheet here. The other process, you can get a bit of extra melting at the front here because you've got a lot of tidal mixing going on in the front of the ice shelf. And then there's also circumpolar deep water sitting out here, and sometimes it can make its way into those ice shelf cavities. And when that happens, you get a lot of melting because the water is now 3 or 4 degrees above the melting point. And when it comes up, it's going to be, it'll cool as it goes up, but it's not going to super cool the way that the high salinity shelf water will. The other thing I should mention here is that the circumpolar deep water has not seen the surface for a long time. It has warmed up a little bit, but not very much over the last century or so. What we're seeing is the change in whether the water gets in the cavity or not. So changes in wind around the Amundsen coast, I believe, is blowing water offshore and pulling more of this water in under the shelf and producing more melting. So if we look at the thinning rates for ice shelves in Antarctica, again, most of that circumpolar deep water is sitting offshore around most of these ice shelves, and it's not actually coming in cavities. As a result, these big ice shelves are not changing much. It looks like Amberley might even be thickening a little bit. But if you look along the Amundsen coast, you see a lot of colors indicating strong thinning, some also up in the peninsula, and then this area around Patton Glacier over here. There's some strong thinning going on in a couple of other glaciers. So much of the thinning ice shelves also corresponds to the area where the glaciers are thinning the most rapidly, and that's again along the Amundsen coast. So this is Thwaites Glacier and Pine Island Glacier. Sometimes when you think of a glacier, you may think of something fairly small, like you might see in Mount Rainier, but the catchment for these each of these glaciers is about the size of Washington, so these are big pieces of real estate. Let me show the speed up on Pine Island because it's a little bit more clear-cut than Thwaites. But basically, this is just showing the speed of the glacier down this flow line. It flows this direction. And you see, even in the interior, you get some speed up. Looking, starting in the 90s, it was about 2,500 meters a year up here, and it's sped up all the way up to 4,000 meters a year. This speed was close to the speed that you need to balance the snowfall, so it was more or less in balance, but now it's well out of balance as it just hemorrhages ice to the ocean. And you can see that thinning here near the grounding line is in here somewhere, and you can see thinning rates of 5 or 6 meters a year. And more importantly, even though this speed-up's only been over the last decade or two, already the influence of the speed-up's propagated inland by a couple hundred kilometers. And we can see that we're still getting half a meter thinning rates here. And even though these numbers are the more dramatic 5 or 6 meters a year, if you actually integrate the Great Basin up here that's thinning at half a meter a year, it's actually much more of the thinning is going on up here than right near the grounding line, where the rates are the most dramatic. This is work by Hamish Pritchard from ISAT that shows, again, we're not looking at isolated one or two glaciers. Pine Island, or often called Pig, Thwaites, and all these other glaciers are thinning to some degree. There's actually thickening going along over here on the Ross Ice Shelf, and most of the glaciers feeding into the Filchner-Ronne, which was one of the big stable Texas-sized ice shelves, is not thinning on the ice shelf and nor of the glaciers themselves. So it really is corresponding well to where the ice shelves are thinning, which would reduce the buttressing. So what we wanted to investigate was whether this kind of change is glaciers fluctuating, maybe jumping back and forth from one bump to another. It could just be some overall fluctuation, maybe driven partly by a decadal scale change in the melt rates, or are we looking, is this indicative of an ice sheet that's where the marine ice sheet instability is kicked in and we're seeing the early stages of collapse? I should mention, because when the press came out about this paper, collapse, different people have different interpretations. We're talking about a structural collapse, so people kind of think of a building collapsing. It's more of a 3, 4, several hundred year time scale, more like in the sense that the Roman Empire collapsed over centuries. This is the Thwaites Glacier bed topography. So this is the ice shelf outlined in black here. These sort of cyan and yellow colors are 600-700 meters deep. That's where the grounding line is, where the glacier first starts to float in here, and it's grounded in a shallower area. But if it can retreat back into this deep basin, that nonlinearity there is going to kick in, and it's really going to start to flow quickly out to sea. So we used a finite element shallow shelf model. So the nice thing about the finite elements is we can concentrate a lot of resolution at the grounding line, and you need to have high mesh resolution, not necessarily the underlying data sets at 300 meters, but to get accurate retreat of the ground line, which means by using finite elements we can sacrifice the resolution in the interior and put it all. If we used a finite difference, I wouldn't have been able to run this on my computers at the resolution that we need at the ground line. And shallow shelf is just an approximated model. There are higher order models. Basically, this is a depth average model, but it still seems to work quite well. We don't have a couple to an ocean model. That's something we'd like to have happen, and several groups are trying to get that happen too. So we use basically empirically derived depth-dependent melt rate. So we looked at, on Pine Island, the flux divergence, and that should more or less equal the melt rate. So we empirically determine a function here. Don't worry about the numbers. The main thing I want to call attention to is this scaling factor m. We tuned m so that for Pine Island anyway, when m was equal to 1, it should keep it in steady state. So we crank up n or crank it down and change the knob on the melt intensity to see how sensitive the glacier is to the melting. And I want to just point out here that m scales the melt rate at a given depth, but not the total melt. So what happens when you first crank up the melt is the ice shelf gets thinner and parts of it get into shallower water where they're going to melt more slowly. So it's always going to increase the amount of melt by turning up the scale factor, but it's not, if I double the scale factor, it's not necessarily doubling the total melt, though it is giving a different ice shelf geometry. One of the first experiments we wanted to do was this is the grounding line retreat with time. So for 250-year simulations, these are the original ice shelf nodes, and then as each one ungrounded, I just colored it by the year that it ungrounded, so you're essentially seeing the grounding line at the beginning of the simulation and the grounding line at the end of the simulation. This first set of experiments, I fixed the velocity because I wanted to get rid of the dynamic response of the ice shelf and just look at what the melting was doing. For the high melt or the low melt, for one of the lower melt ones, the grounding line retreat's about the same. It's not melting. The melting itself is not forcing the ungrounding. It's the dynamics that's doing that. And to some extent, this is the amount of ungrounding you would get with sort of the current velocities that we're seeing. Or actually, I should take that back. The 1996 velocities we started the model with. Then these next simulations, we just turned up the amount of melt, and you could see we lowered the amount of melt, even sort of half what we thought might be something like steady state for Pine Island. So this is quite a low rate, and it still continued to unground and actually speed up. And we got more when we used our nominal value, and with the highest melt rate, we got quite a bit of retreat. This is starting to now retreat into near that trough. The other thing we did some experiments where we allowed the margins of the ice shelf, which are holding the ice back, to weaken. We would expect some mechanical weakening. And it just basically demonstrated that the weaker margins, even for the lower melt rate here, give more grounding line retreat because the ice shelf is having less of a buttressing effect. It's that last case. Just to show what this is what the thinning rates for the n equals 3 simulation, and you can see they're actually quite variable as little bits unground, but it actually pretty quickly diffuses into the ice sheet. Most of these simulations, the losses are increasing. They're just sort of in this blue area here, again, integrated over the basin. But again, you can see they pretty quickly migrate inland. Also, if you look at the kind of variation, you can imagine how hard it is with a satellite altimeter that's flying for 5 years to actually avoid aliasing signals when you with that kind of variation. So these are the various losses for 250 years. Gigatons on the left, which may not make much sense, but it's a little more intuitive to look at the amount of sea level equivalent. So if we crank up the melt with this black curve, we get up to about 0.5 millimeter of sea level rise. It starts to rebound a little bit, but then actually, I'll show it in the next plot, it actually starts to go to a high rate of loss. And everything looks roughly the same, but it more or less scales with the melt rate. These blue curves would look like this when we extend them out. I'll show that in a second. One thing that was very encouraging about these simulations was we actually do have 18 years of observations of the losses to compare, and when we compare it with the orange and black curves, these n equals 3 and 4 simulations, these curves pretty much track what actually happened. We initialize the model with the data from this initial point, but all of this is the model sort of independently doing what the observations do. And interestingly enough, when we went and looked at what these the total melt on the shelf was for these values, it agreed very well with the estimates from a couple of independent observations. In fact, the estimates from the independent observations were 60 to 90 gigatons a year, and our estimate was something like 72, so we fell right in the range. When we run out for 1,000 years, all but the very low melt simulations, at some point hit that deep basin, and then things just, all hell breaks loose, and rates go well over a millimeter a year. We stop the model at that point because it's a basin scale model, and it's not interacting with the rest of the ice sheet. But we would expect once that happens, that it would start to pull in ice from the surrounding basins, and potentially the whole ice sheet at that point, West Antarctic ice sheet would go, and potentially over a few decades or less. But the timing of when this happens varies substantially from something like 200 to 900 years. I think if I run these simulations longer, eventually even the low melt situations would go, indicating that sort of irrespective of the melt forcing the ice sheet is in retreat, it's probably not going to stop retreating. It's just a matter of how long it takes to retreat. And there was a lot of press about, it's irreversible, we should throw up our hands, but the important point is that, well, if all of West Antarctica went in 200 years, that's 10 feet of sea level rise, or 6 inches a decade. If it took more on sort of the 1,000-year time scale, we're looking at a foot per century, which is sort of double the current rate we're seeing now. Definitely, it's not a reason to just say it doesn't matter, we can burn all the fuel we want. So to summarize, West Antarctica, the ice sheets are sensitive to ice-ocean interaction as nearby waters warm, or potentially I should more say as nearby waters, warm waters get transported under the ice shelves. Mechanical integrity of the ice shelf is important. We have a pretty good feel for the ice dynamics. There's always higher order models we could run, but we really still have a lot to learn about how, and this is getting out of my field, but how water temperature and transport will change around the ice shelves. Who knows what the winds in the Amundsen coast are going to be doing in 100 years. Ideally, we should be coupled to a global climate model, but again, it's not my forte, but I'm not sure exactly how much uncertainty that climate model for the winds would reduce. There was a paper showing that the Filchner-Ronne ice shelf should start melting due to the wind changes in the Weddell Sea, and I know there's a lot of controversy. A lot of people felt that they hadn't got that right. But ultimately, we would want to be able to couple to a climate model so we can test the various climate scenarios. And I think a lot of progress can be made in the near term with just coupling to a smaller scale ice shelf with an ice cavity model where we could just force it with some other ocean on the boundary. And waste is definitely likely in the early stages of collapse. Our model could be wrong, it could be wrong, but it really does look like the ice sheets, the collapse has started, and it will only get faster with time. So with that, I can take questions.
I was wondering, with those large speed-ups in Greenland for ice velocities, if you have any idea, like, if there's atmospheric or ocean variables that like correlate with that or help explain that, or if it's all the base, sort of the bed.
Well, the problem is they all, it warmed up at the time that the glaciers started speeding up. And so, yeah, the temperature, surface temperatures warmed up, and both the winter and the summer temperatures warmed up, and then the sea surface temperatures warmed up, and the ocean deep temperatures warmed up. So there's this warm up and there's a speed up of the glacier, but any of those variables would correlate, but it wouldn't necessarily be a causal relationship. Or it could be 1/3 of each of those things, or it could all be the deep water or the surface temperature.
Right. So that's like on the seasonal scale, but I guess I'm wondering like year to year if there's any like extra warming or anything that can help explain it, or if it's not.
Well, I mean, year to year, there's been a sort of a trend over the last decade of warmer temperatures, and there's also been a trend of increasing speeds when you average all the glaciers together, which should start to get rid of some of the variability of individual glaciers. So there's sort of two upward trends in both directions, I think.
Okay.
Talking about just kind of the observation that people looking at across Fiscal Bay, I think, by dog sliding, is that essentially unprecedented, or is there kind of oral record of that occurring in the past? I mean, is there a possibility that it's associated with oscillation rather than directional change, or is it?
The Greenland, I'm not a climatologist, but Greenland does, I mean, it did get a lot warmer in the 30s, not so different than today. So I don't know what they were doing in the 30s, if they were taking a boat or a ferry, but, so I don't have a great answer for that, but definitely Greenland, it's not just, well, whatever global trend there is, there's also a huge amount of multi-decadal variability on top of that.
So let me start this question with a large caveat. I'm not a proponent of geoengineering, certainly, but some folks suggest that doing sulfur injection would help to reverse some of the effects of the ice sheet collapsing and so on. But it seems your research seems to suggest that this process is going to continue regardless, right? It's just about the speed that it will continue.
Well, if you can reduce the rate at which warm water gets in the cavity, it does show that it will reduce the melt, and that the ice sheet would come down over a longer period. Now, if we went into full glacial conditions right now, probably it might stop, but I don't think we can even geoengineer that.
Right.
It is interesting when you publish a paper that gets this much press, like all of the ideas that people send you. I was getting emails about putting these big windmills that would pull water up and spray it on the surface so you could just build up all the sea ice, and there were all sorts of interesting emails I got.
Great. So with that, I think we can continue the discussion outside. There's refreshments out there. So let's thank Ian again.